8 years in semiconductor thermal simulation. 8 years of heat, pressure, and late-night deadlines that bled into one another. I sat at my desk, the glow of the monitor reflecting in my tired eyes, and realized I was finished. My hands rested on the keyboard, but they were shaking. Not from excitement, but from exhaustion that sleep could no longer fix. I had reached the edge of my capacity. Every line of code, every thermal model, every project report had become a weight I could no longer carry. My lungs felt tight, and my mind felt like a processor running at peak load without a cooling system. The air in the lab was stale, smelling of ozone and recycled heat. I looked at the screen, at the complex geometry of the latest design, and felt absolutely nothing. No drive to solve the next problem, no desire to prove my worth, just a hollow certainty that this path was leading to a dead end. I stood up, pushed my chair back, and felt the floor tilt beneath me. I had given everything to this career, and in return, it had taken every ounce of my resolve. It was time to walk away. I did not walk away. Not yet. The team had been pulled onto a high-end GPU module project, a task of immense professional magnitude. It was the kind of hardware that defined a company's year. If this module failed, the fallout would be absolute. The stakes were written into every memo and every meeting. My director spoke of market dominance and performance targets, his voice thin with the tension of the deadline. We were operating at the bleeding edge of thermal management, pushing silicon to its absolute limit. Every engineer in the lab felt the gravity of it. We were not just building a product, we were defending our collective reputation. The module sat in the center of the clean room, a silent, complex piece of engineering that held our careers in its delicate circuitry. We were told that failure was not an option, but in that high-pressure environment, the margin for error was non-existent. I watched the team hover around the test benches, their movements precise and hurried. We were locked into a cycle of immense scrutiny. The pressure to succeed was a constant hum-like vibration in the room, making every minor adjustment feel like a high-stakes gamble. The module was ready for the next phase of reliability testing. We waited for the results, unaware that the catastrophe was already waiting for us. The reliability chamber hummed, a low-frequency drone that signaled the start of the first thermal cycle. We watched the monitors, our attention fixed on the sensor readouts. Then, the alarm cut through the silence, a sharp digital chirp. The first cycle failed. We reset the parameters, convinced it was a calibration glitch. The chamber ramped up again. Temperature climbed. Heat soaked into the silicon, and the module pushed past its thermal threshold. Another alarm. The second failure hit the log. The air in the room grew heavy. We moved faster, checking connections and verifying power delivery, but the data remained stubborn. The third cycle began with an unnatural intensity. We stood motionless, watching the graph climb toward the breaking point. It peaked, shuddered, and died. A third failure. The realization dawned on us in the sudden, suffocating quiet of the lab. One more cycle. We forced the system through a fourth run, hoping for a different outcome, but the result was identical. The data was absolute. 4 cycles, 4 failures. The hardware was not just underperforming, it was fundamentally incapable of handling the thermal load. The project was no longer a development task. It was a crisis. The director paced into the lab before the logs had even finished uploading. He did not look at the graphs. He did not ask for the sensor data. He walked straight to the test bench, tapped the module, and declared the culprit in a single, dismissive sentence. It is the thermal interface material. He ignored the possibility of a routing issue or a substrate bottleneck. To him, the fix was simple. Swap the grease, reapply the compound, and run the cycle again. He treated the complex, multi-layered failure as if it were a simple hardware assembly problem. We tried to voice our concerns about the internal heat density, but he cut us off with a wave of his hand. He demanded we strip the existing material, clean the interfaces, and retest immediately. He locked us into a narrow corridor of action. Every minute spent scrubbing thermal grease was a minute we were not investigating the root cause. We were being directed to treat a systemic architectural flaw with a surface-level remedy. He stood over the bench, monitoring our progress, ensuring we followed his prescribed path to the letter. It was a cycle of forced repetition. We were no longer engineers solving a problem. We were technicians executing a blind guess. The lab atmosphere shifted from analytical to strictly procedural, dictated by an incorrect assumption that we were powerless to challenge. The directive was absolute: 9 in the morning until 2 the next morning. For 11 straight days, he did not care about the lack of progress or the empty data logs. He wanted hours logged and materials swapped. The first day felt like a marathon. We arrived as the sun rose and stayed long after the building went dark, our eyes stinging under the harsh overhead lights. By the third day, the routine turned into a blur of gray metal and chemical solvents. We arrived at 9, performed the same repetitive tasks, and collapsed into our chairs at 2. There was no time for analysis, only for the physical labor of cleaning and remounting. The lab became our entire world. We stopped tracking the days. The clock on the wall was the only heartbeat in the room, ticking toward a midnight that never brought relief. My coffee turned cold, then bitter, then became a necessity just to keep my hands from shaking. We were exhausted. We were mentally drained. Yet, every morning at 9, the director was there, pointing at the clock, demanding more cycles. The process was a meat grinder, and we were the fuel. 11 days of this, and we were no closer to a solution than when we started. Our days became defined by the smell of industrial solvents and the sight of ruined components. We spent hours scraping thermal grease from the heat sinks, the chemical sting burning our nostrils. We would lay out the new interface materials, press the module together, and bolt it down to the test rig with mechanical precision. We waited for the thermal cycle to complete. We watched the monitor for the failure threshold. It always hit. Failure. We would unbolt the module, peel away the scorched material, and start the cleaning process over. It was destructive testing in its most literal sense. We were tearing apart hardware that was perfectly functional in every other aspect, hoping that a different application of grease would defy the laws of physics. We piled the discarded materials in the corner, a growing mountain of copper, failed sensors, and torn gaskets. It felt like alchemy performed by someone who had forgotten the spells. We checked the torque on every bolt. We measured the thickness of the application with calipers, and we repeated the cycle. The logic of the process had evaporated. We were simply moving grease from one surface to another, hoping the result would magically change, while the real issue remained buried deep within the chip, untouched and ignored. By the 11th night, the fatigue moved from my mind into my bones. I reached for the torque wrench, and my fingers betrayed me. They danced in the air, a rhythmic, uncontrollable twitching that made the simple act of gripping steel feel impossible. I leaned against the workbench, waiting for the tremor to subside. But it only grew worse. Every muscle in my arm was screaming from the static tension of holding the same position for hours. I looked down at my hands. They were raw, stained with grease, and vibrating like a plucked string. I tried to steady them against the edge of the metal table, but the vibration rattled the tools scattered across the surface. It was not just the lack of sleep. It was the crushing weight of a process that required precision while actively destroying the ability to perform it. I took a deep breath, clenched my fist until the knuckles went white, and tried to force the shaking to stop. It lasted for a heartbeat, then the tremor returned, violent and insistent. I was no longer an engineer. I was a broken component, just like the chips we were testing. I stood there, in the quiet of the lab, watching my own hands refuse to obey, and realized that my body had reached its absolute limit. The 12th day dawned with a clarity that felt like a slap. I stared at the latest failure report, then at the mountain of discarded parts. The realization did not arrive as a sudden thought, but as a hollow, sinking weight in my chest. We were not engineering anything. We were not solving problems. We were sitting at a table with our eyes closed, throwing dice against a wall, hoping the numbers would align by pure chance. The director called it reliability testing. I saw it for what it had become: high-stakes gambling with prototype hardware as the currency. Every bolt I tightened was a bet. Every thermal cycle was a roll of the dice. We had abandoned the data, the physics, and the logic that defined our profession, replacing them with a frantic, desperate hope that the next attempt would be the one. I looked at the team, faces gray under the fluorescent lights, and saw the same dead look in their eyes. We were no longer seeking a solution. We were waiting for a miracle to bail us out of a broken process. The math had been discarded. The analytical tools sat idle on our workstations, ignored, in favor of this primitive, destructive guessing game. I stood in the middle of the lab, surrounded by the debris of 11 days, and finally understood that we had lost our way entirely. The lab began to thin out as the clock ticked past 2 a.m. One by one, the others packed their bags, their movements sluggish and heavy with the weight of the last 11 days. They did not speak. There was nothing left to say. I watched the door click shut, the latch echoing in the sudden, expansive quiet. At 2:30 a.m., the room was finally mine. The fluorescent lights hummed a low, erratic buzz that seemed to vibrate against my skull. The rows of workstations stood empty, littered with the wreckage of our failed experiments, charred components, tangled test leads, and piles of discarded documentation lay scattered like debris after a storm. I walked to the center of the room. The silence here was not peaceful. It was heavy, suffocating, and absolute. It pressed in from the corners, amplifying the sound of my own shallow breathing. I stared at the dark screens of my colleagues' monitors. They were dark, inactive, and cold. The air smelled of ozone and stale coffee, a sharp, chemical scent that clung to the back of my throat. I was entirely alone. The pressure of the project, the exhaustion of the team, and the failures of the last 2 weeks all converged in this stillness. I stood there, motionless, waiting for the final pulse of courage to take hold. The path forward was clear, and it required me to abandon everything I had been told to do. I moved toward my primary workstation. My chair scraped against the floor, a jarring sound that sliced through the stillness. I sat down and stared at the monitor. The screen glowed, casting a harsh, artificial light onto my hands. I reached for the mouse, but stopped. To run this simulation was to admit the director was wrong. It was a direct violation of every order given during these 11 days. I looked at the desktop icons, specifically the ANSYS IcePack shortcut. It sat there, a silent tool of logic in a room governed by blind guessing. My pulse thrummed in my fingertips. I clicked. The application launched, a series of windows cascading across the display. I ignored the standard workflow prompts. I bypassed the project folders designated for the official reliability tests. I navigated to the raw GPU module layout files. The very data we had been told was irrelevant. I dragged the files into the workspace. The software parsed the geometry, recognizing the complex assembly in seconds. I felt the weight of the decision settle into my bones. There was no going back now. I checked the boundary conditions, entered the power parameters, and ignored the warning dialogues regarding unofficial simulation parameters. My cursor hovered over the Run button. I took a breath, held it, and clicked Start. The process began. The progress bar appeared, a thin blue line cutting across the screen. It moved, then stalled. then crawled forward with agonizing slowness. I leaned back, my chair groaning under the shift in weight. The workstation fans began to spin faster, their pitch rising from a low hum to a sharp, high-frequency whine that filled the lab. The machine was working now, crunching millions of mesh nodes, solving equations that had been ignored for weeks. I watched the time counter. 10 minutes passed, then 30. The screen flickered, casting a rhythmic, pulsing light across the workbench. I could not sit still. I paced the small aisle between rows of desks, my footsteps echoing against the linoleum. Every few minutes, I circled back to verify the status. The simulation was still running, consuming every cycle the processor could provide. Outside, the world remained dark, detached from the heat and pressure building inside the silicon module. My mouth was dry. I checked my watch, then checked the screen again. The estimated completion time barely shifted. It was a brutal, mechanical indifference. I was betting my career on a set of mathematical proofs, and the only thing I could do was watch the timer tick. Each second felt like a physical weight, pulling at my nerves, forcing me to confront the absolute silence of the room while the computer digested the hidden truth of our failure. The fans abruptly cut to a low, dying whir. The high-pitched whine vanished, leaving a ringing silence in my ears. I stopped mid-stride. The screen blinked. Once, twice, and then the interface transformed. The raw data vanished, replaced by a complex thermal contour map. I stepped forward, my hands gripping the edge of the desk until my knuckles went white. The image was undeniable. Deep, saturated red concentrations bled across the display, clustered directly beneath the die. I leaned in, my face inches from the glass. The intensity of the color was shocking. It was not a diffuse, manageable warmth. It was a violent, concentrated spike of thermal energy. My eyes traced the boundaries, searching for a flaw in the model, but the software had mapped the heat with surgical precision. The focal point of the failure stood out in stark contrast to the cooler surrounding regions. I stared at the screen, the light reflecting in my pupils, and felt the blood drain from my face. The clarity was absolute. This was not a material issue. It was not a grease problem that could be fixed with a fresh application or a torque adjustment. I had spent 11 days scraping, cleaning, and testing, all while the solution sat hidden in the geometry. The truth burned on the monitor, a map of my own wasted effort, and for the first time in weeks, the confusion dissolved into pure, cold certainty. I clicked the cursor to strip away the outer casing layers, exposing the internal routing of the substrate. The software rendered the cross-section in high resolution. There it was, a dense grid of copper traces clustered beneath the die, bunched together with no room for thermal dissipation. It was a textbook current bottleneck. The electricity was forced through a restricted path, causing resistance to spike and heat to concentrate in a single, trapped zone. It was effectively an oven, sealed tight within the module. Every time we increased the power during testing, we were just fueling the fire inside that structural trap. The thermal material we had been swapping out, the grease we had been obsessively cleaning and reapplying it was never the culprit. The material was doing its job, but the substrate design was inherently flawed from the start. I rotated the 3D model, watching the heat map shift as I adjusted the current density parameters. The red zones intensified, pulsating with every simulated watt. The physics did not lie. We had been fighting the wrong enemy for 11 days, tearing apart the hardware while the real failure was buried deep in the substrate layout. The sheer waste of time hit me with a dull, heavy finality. I had the proof, the data, and the answer, all staring back at me from the glow of the monitor. I looked at the clock. 5:40 a.m. The lab was dead quiet, save for the rhythmic hum of the server racks. My hands were still shaking, not from the cold, but from the raw adrenaline of finally seeing the truth. I grabbed the mouse, my movements precise and deliberate. I framed the thermal plot to highlight the substrate bottleneck, adjusted the color scale to ensure the temperature spikes were impossible to ignore, and triggered the capture tool. The shutter sound of the screen grab felt like a gunshot in the silent room. I opened the executive group chat. The last message was from the director, sent 12 hours ago, demanding an update on the next round of destructive testing. I ignored it. I attached the high-resolution image, added a single line of text explaining the internal routing failure, and hit send. The message icon blinked, then turned to a delivered status. It was 5:45 a.m. I did not wait for a response. I did not wait for validation. I closed the laptop, pushed back from the desk, and stood up. The weight of the last 11 days lifted as I turned off the monitors. I walked out of the lab, leaving the broken hardware and the grease-stained benches behind, and headed for the exit. The data was live. The guessing game was over. I woke up to the buzz of my phone against the nightstand. It was 10 a.m. I stared at the screen, heart hammering against my ribs, waiting for the fallout. The executive group chat icon was glowing with a red notification badge. I tapped it. The screen refreshed. My screenshot of the thermal plot was sitting there, a bright, undeniable red mark against the dark background of the chat. The message was sent at 5:45 a.m. It was now 4 hours later. I scrolled up. Nothing. No angry replies. No defensive excuses. No demand for a physical retest. Just the image, frozen in the stream. I counted the minutes. 10 minutes passed while I watched the screen, my thumb hovering over the glass. The silence was heavier than any argument. It was the sound of a foundation cracking. Those 10 minutes were not a delay. They were a reckoning. They were the sound of every executive in that group realizing they had authorized 11 days of useless, destructive labor based on a guess. My breath hitched as the typing indicator finally flickered to life. The director was writing. The silence was over, and the shift in power was absolute. I leaned in, watching the cursor blink, knowing that whatever came next would change everything. The text appeared on my screen, brief and clinical. Why was this simulation not run at the start? I read it 3 times. The director was not asking for a technical clarification. He was asking for a justification for the 11 days of wasted labor he himself had commanded. The question hung there, stripped of any authority. It was an admission of defeat. He had no answer for why we spent hundreds of man-hours scraping grease when a 3-hour simulation could have provided the truth. I looked at the words, feeling the heat of the screen against my thumb. It was the sound of a system designed to fail. By asking that, he exposed the entire industry's reliance on brute force over intelligence. We were never engineers to them. We were lab rats performing manual tasks in a loop of trial and error. The question defined the collapse of our process. It was the final nail in the coffin of the old way. I did not reply. I did not need to. The question itself had already provided the only answer that mattered. The process was broken, and he knew it. That single question confirmed the rot. We were trapped in a cycle of trial and error, treating high-end hardware as a guessing game. Every day, I watched brilliant minds scrape grease and swap materials while management demanded physical fixes that defied logic. We spent weeks cleaning broken geometry and guessing material properties, ignoring the very tools designed to solve these problems. It was a waste of intellect, a systematic grind that turned engineers into manual laborers. The industry remains addicted to this brute force approach. They prioritize the visible, messy work of the lab over the invisible, precise work of simulation. It is a culture that rewards suffering instead of accuracy. I saw the toll it took on my team, the hollow eyes, the shaking hands, the complete depletion of creative drive. We were sacrificing health to cool down chips that could have been optimized in hours. This is not engineering. It is a failure of vision. We are losing talent because we refuse to bridge the gap between CAD data and real-world physics. It stops being about innovation when you are just running in circles, waiting for a prototype to fail so you can guess again. I spent 3 years debugging my own workflow to bridge the gap between static CAD data and the reality of thermal physics. It was a slow process of rebuilding from the ground up. Today, I do not ask for permission to simulate. My team mandates a thermal and stress simulation gate before a single prototype is ever manufactured. It is a non-negotiable step in our R&D cycle. If the model fails the digital test, it does not reach the production floor. We shifted the burden of proof from the physical lab to the digital environment. It was a friction-filled transition. Management pushed back, demanding physical parts to show progress. But I held the line. I pointed to the data, to the cost of those wasted cycles, and to the stability of our current designs. We stopped guessing. We started calculating. This gate is the barrier between our current efficiency and the chaos I once endured. It forces every engineer to solve problems in the virtual space where errors are cheap and fixes are fast. We turned a traumatic failure into a rigid, repeatable standard that protects our time and our output. The machine does the heavy lifting now, and we do the engineering. The results appeared in our quarterly logs within 6 months. We reduced late-stage firefighting by 60%. That is not just a statistical improvement. That is months of saved time, hundreds of hours no longer spent in the lab chasing ghost thermal issues. We effectively eliminated those 2 a.m. sessions. The lights go off in our facility at 6 p.m. now. My team is no longer exhausted. They are sharp, they are focused, and they are doing the work they were hired to perform. We stopped the cycle of destructive testing as our primary development method. When you move the failure point to the screen, you reclaim your life. Your value as an engineer lies in the quality of your decisions, not in the hours you spend suffering for a faulty process. I look at my lab now, and I see clean benches, quiet equipment, and engineers who have the energy to think. We proved that predictive engineering is not a luxury. It is a necessity for anyone who wants to survive in this industry. We trade guesses for certainty and burnout for sustainable output. The data confirms what I suspected 3 years ago. When you let the computers do the heavy lifting, the human element regains its purpose and its health. I have compiled my entire thermal simulation SOP into a single, actionable guide. It covers everything: geometry simplification, precise boundary condition definition, and data presentation that actually convinces management. I am tired of seeing brilliant minds burn out because they are tethered to outdated R&D methods. You do not have to be the martyr of your own project. You do not have to sacrifice your health to cool down chips while your tools sit idle. If you are ready to replace brute force testing with predictive engineering, I want to help you make the switch. Comment SOSs below this video right now. I will send the framework directly to your inbox so you can start reclaiming your time today. Stop guessing. Stop the 2 a.m. cycles. Let the computers do the work they were designed for, and give yourself the professional life you actually earned. The transition starts with one decision. Leave the SOSs comment, get the guide, and leave the manual labor of broken processes behind you for good. Your career is worth more than the mistakes of a faulty system. Let us get to work.